Cool. Welcome to this talk and thank you for attending. As said, I'm Käldström, and today I'm going to talk about the edge. Let's see. So this is the standard slide that I show before who am I. So, well, I'm working for Weaveworks, have been a contractor there for a bit more years, and I've been heavily invested in the Kubernetes ecosystem, contributing upstream a lot, and going to speaking at KubeCons and doing that kind of stuff. And now at the moment I'm actually studying full time at university, my second year. Cool. So before diving in, this is just a small clarification or warning in terms of expectation management. This talk doesn't talk about MLOps directly as is. Instead, it's more like what are the foundations for being able to do MLOps on the edge. So like if you would now be to deploy, well, there's one example of they have like tens of thousands of sensors across the world's longest bridge, and there they have a lot of compute. And if you were to deploy that kind of stuff, what do you need to think about to keep those edge locations secure and automated and all these things? So yes, and I will dive into quite a lot of different topics, but I won't dive deep into a single topic. So it's more like inspiration for you to look more on investigate these topics more. Okay, so the talk is divided into 6 chapters, and the first part is 3 chapters on edge security, and the second part is 3 chapters on edge automation. So let's start with secure the boot process as the first chapter. So what is hard with what is hard with booting or booting a machine? Well, it's correctness and openness of the boot binaries. So if you get just proprietary closed source binaries, how can you be sure that it's not outdated, or it doesn't have a backdoor or a CVE or some other nasty thing like that? That kind of verification process becomes really important if you're deploying a large system. Then deploying duplication of important drivers is also kind of across the different bootloaders is a problem where most of the bootloaders are written in C, so a memory unsafe language, and implementing a UDP driver, for example, is extremely hard. And on top of that, you have like 0.5 MB of space that you actually can do anything. So getting all that kind of settled and then doing one UDP implementation, for example, for each different vendor that has their own bootloaders, that becomes a lot of different bootloaders, and they could be so much better off by sharing code. So that's the second problem. Then introspection of the boot flow. So how do you know that you have booted the right binaries in order and you didn't have something malicious in between there that kind of hijacked the boot flow? That is one problem. And then remote verification of an edge node. How can you ensure that as a remote actor, so if you're in the cloud and you have a lot of edge nodes out there, how can you know that, well, the edge node actually are legit, they are in a well-known state, they are safe? How can you know that there is no person that has gone and messed with them? So those are the 4 topics that we're going to look at. So the first thing is let's see there, on-chip bootloader in read-only memory. This is unchangeable. It's burnt when into the CPU or system on chip when it's manufactured, and has very limited functionality, or it should have very limited functionality. The on-chip bootloader figures out that where is the hardware initialization bootloader, and this is often loaded from some SD card, some SPI flash, some EEPROM, or similar by the first bootloader. And the second one is often subject to really tight size constraints in the CPU, because it's running in the CPU cache or in the static RAM that is often limited to something like half a megabyte. And what is the purpose of this second bootloader? Well, it is to initialize the RAM, so the dynamic RAM, and among other things, depending on the system on chip. But generally it does this, and also it has on ARM it's called an ARM stub, a short piece of hardware initialization code. So this is the purpose of the second bootloader, and open source projects that do these things is U-boot, and specifically U-boot SPL, and then this is popular on ARM devices, and then core boot. And the second bootloader loads then a raw executable straight into the newly initialized RAM. And this raw executable can be something like Linux or another bare metal executable like Tiano Core EDK2, which is an open source UEFI implementation, or U-boot, for example, that is pretty popular. And yeah, this is loaded into RAM and executed by the second bootloader. And it's the job of the second bootloader to find this executable as well. So there's core boot that I was talking about. This is popular with x86 devices. For example, a lot of Chromebooks use core boot for better security, but it also supports some ARM boards and other platforms. One of the founders of core boot went on to create ORBoot, which is core boot but with all the C removed, and all the C is instead rewritten in Rust. And then U-boot is the classic ARM single board computer bootloader that is essentially everywhere in this space. The open source firmware movement is really exciting. I highly recommend that you join the Slack link there below. I will share my slides in the chat and online. So to understand this better, let's take an example. So we have the on-chip read-only memory bootloader, and this is executing in the GPU or the Broadcom system on chip. That goes to the EEPROM of the Raspberry Pi 4 and gets the executable from there and starts it, again still in the GPU. And then this EEPROM bootloader can get the next boot files from TFTP, so the network. This TFTP uses UDP. Then the SD card can get the boot file from USB, SSD, a lot of other things. I think even NVMe these days. And when it has the boot files, it goes ahead and runs the main firmware of the video core that is a Broadcom GPU on the Raspberry Pi, and that is called Start Elf bootloader. And this is a bit larger, but all of these are proprietary. And then config.txt you can use to configure the bootloader. And yeah, once we have this, it goes ahead and initializes the RAM. This is an important, I have separated this because this is an important step. Now, after the RAM is initialized, you can run the ARM stub, and which initializes some CPU features like generic interrupt controllers and that kind of stuff. And when this is done, then the CPUs are set up, and now we can run the Linux kernel, or as I said before, Tiano Core or U-boot. But we see that there's not that much green here that is open source, but mostly red. So if we would kind of look at some other board than the Raspberry Pi, which is fixed to this, how would an ideal solution look like, or scenario? Well, the ideal in terms of pragmatism, we just have to, I guess, accept that the system on chip read-only memory bootloader is probably going to be closed source anyway. But it's fine because we really, in the earlier example, the first EEPROM bootloader is doing a lot of stuff. It can do network, it can do SD card, USB. These things are not easy to do, and it does them all at a very early stage in the boot. But if we limit this to something simpler like SpyFlash or just SD card, for example, then now we can have a fairly limited set of functionality in the on-chip ROM, and then that is unchangeable, so we can't update it. So, and this is important because, like, if you if you put something in the on-chip ROM and it has some really bad security vulnerability, then essentially you can't use it anymore, at least not securely. But then instead of but at this point now we can load U-boot from the SPI flash or SD card or something like that. We can load in U-boot SPL or some core boot or the other things I was talking about. And this can now initialize the RAM and do all of the things that we need. It can include some ARM stub, other hardware initialization procedure to set up the cores, and then we can run the kernel or the main executable that we want. But U-boot SPL is good in this sense that it can figure out the RAM initialization using open source code. So this is better in terms of now we have most of the stuff executing on the CPU, which is easier to write code for and more generic. And then we have U-boot, which is the de facto standard on ARM SBCs. Cool. But now the observant listener might see that now we're missing out on net booting, actually, because now there was a net boot option before using TFTP earlier, but that isn't part of this picture. But I'm gonna touch upon this a bit later. But there is a solution, and it's also the solution is also more secure than TFTP, which is a protocol that doesn't have any authentication or authorization or encryption at all. So we can do better in these terms. But now we have addressed problem 1, correctness and openness of the boot binaries. So we started from something that has mostly closed source code, and then change it to something that has a bit more, or find alternatives that is more open source. And for example, the ROC chips support U-boot SPL as I showed in the more ideal scenario. Then, because this is a security talk, I'm gonna next talk about Trusted Framework A, or TFA for short. And this is similar to Intel SGX, which is essentially a thing that partitions the CPU into a secure and non-secure part. And well, TFA implements a subset of the SGX features, but still, this is what we have on ARM. And the secure part is, or the secure world is managed by OPT, which stands for Open Source Trusted Execution Environment. And you can write applications in this OPT kind of world using Rust or Go. So that's great. So you have memory safe language support, and then there is a communication channel. TFA provides a communication channel between the secure world and the, say, non-secure world, which is your normal Linux in this case. TFA is packaged as this ARM stub that we saw earlier, that is run right before the CPUs are set up. And so now if we change the picture a bit, then U-boot calls, instead of just a generic ARM stub, it calls TFA. And TFA partitions the next step into a secure world and a non-secure world, and starts both of them and facilitates a communication channel between them. Cool. So that is the first chapter. Then the next one is securely net booting the OS, because I was talking about this network booting before. How do we solve that? Well, Linux boot is a project that has a pretty simple at its core idea that instead of all the bootloaders duplicating the work on the device drivers and custom features and that kind of stuff, everybody can use Linux as the firmware instead, and reuse by design then all of the device drivers that Linux has. So this can be seen in this picture, that after the firmware has initialized the hardware and memory is initialized, then all of the, regardless of where you're coming from, the low-level bootloader, the second one in the earlier diagram, would call Linux as the third step. And Linux, in that you can write in any Python or Go or JavaScript your, so to say, firmware, and find the next thing to boot from anywhere. And then when you have found your OS that you want to boot, then you can use a thing called kexec. That is a function call to Linux to say that change the running kernel without rebooting, and that gets you, as in the picture, like it goes from Linux boot then to the real OS. And Linux boot, the purpose is that it should be really minimal. So like just a couple of megabytes of Linux, and you really strip it down to the bare bones. So now compare this traditional UEFI initialization flow with the Linux boot initialization flow. So in the beginning, there's 3 or 4 boxes. That's, I guess, okay. But then in the fetch OS to boot part of the UEFI on the left side, there's a lot of different things, and a lot of different custom things for each UEFI implementation. Then if we just replace all of that with Linux, the picture becomes quite much cleaner. And then after that, you kexec and you're in the target OS. So this has a drawback. It has the drawback that you can only boot Linux as your target OS. If you want to do Windows or Mac or something else, you still need UEFI. But for the case of running Linux as target OS, this works really well. So how do you, I said that you can write your firmware in Python or JavaScript or whatever. How do you do that in practice? There is a project called uroot that is a kind of packaging mechanism for you to do to do this easier. So if you have your Python script, you can use uroot to include it into the Linux boot build. So it's more kind of a build system, and then it has a lot of common boot logic written in Go, so that you can reuse. And it looks, if you boot into Linux boot and hasn't specified a boot script, then it drops you into a shell and says that, well, here you go, like type any commands you want, and these commands are then written, are the boot logic written in Go that you can proceed with. And now if we modify the picture again, what does it look like? Well, we have on-chip ROM loads uboot SPL or something similar. It runs TFA, sets up the secure and non-secure world. TFA runs Linux boot, the micro Linux here, and then Linux boot runs uroot, which is written in Go and has maybe some of your custom logic for the boot flow, or you could, what you earlier would have called firmware. And then that uroot logic finds the real Linux that you want to boot and kexec into that. So now we can do network booting. And now that we have these kind of more advanced capabilities, how advanced can we go? So the update framework is a framework for securing software update systems. It contains a set of steps to follow to ensure that software updates or software artifacts are not, at least, well, easily compromised by attackers. So there's a lot of common pitfalls that you can run into when trying to upgrade a file or trying to download something from the internet that you might not have thought about if you didn't follow this framework. But if you have followed this framework and the checklist, then you can be pretty sure that you're well guarded against the most common attacks, at least. It's a graduated CNCF project, and it's used in all of our favorite Docker pull and push through a project called Notary. And it's also used in many other places, and BottleRocket is an operating system that is using this as the update mechanism, as an example. And then a bit more about containers. Open Containers Initiative is essentially the container standard that is donated to the Linux Foundation by Docker in 2015, and it provides the specs for what is a container image, how do you run a container, so isolation, and then how do you distribute a container, so distribution. So it contains all of the three parts: packaging, isolation, and distribution. And it's actually pretty interesting to see that OCI, the distribution part, is evolving into a generic artifact distribution mechanism with Dave's Auras project. So now that we have all of these, how could we put something together that boots in a new way and maybe not seen before? So if we combine Linux boot and the OCI part that I was talking about, then we could essentially, you could build your OS image using a Docker file, and then you want to net boot your computer, so your SBC, for example, in a modern way. So what's going to happen is that we actually do a Docker literal Docker pull in when booting the machine. It gets the content and starts that. So I'll come back with a picture of this. And the OCI provides image packaging and distribution, so we don't have to reinvent the wheel. We can write all of this firmware in Go. There's already pre-made libraries and everything. And if we don't want to use the container OCI container format as the image, then we can just distribute any, for example, QCow2 image using Auras instead. So this is what it looks like. Linux boot starts in OCI boot, that I call it. This is not yet implemented, but it's an idea that I'm going to explore very soon. You provide some pull secrets. OCI boot does a normal OCI pull from some place on the network, then extracts the OS image from there, loads it into RAM or into disk, and then does a kexec, and boom, where we have figured out the target OS. And now, compared with the earlier thing, which only had TFTP or UDP support and no security or nothing, this has many benefits. And all the complex netboot logic is written in Go, so a memory-safe language. We have reused all the device drivers from Linux, so no need to start writing a TCP driver for me when I want to do this now. This works regardless of the kind of compute or manufacturer or CPU, because Linux takes care of all of that. And then Notary is used behind the scenes for the kind of cryptographic verification, so I don't have to do that either. But if I would want to do the cryptographic verification myself, I could use TUF. So TUF, as said, is a checklist of what to do for more advanced trust and delegation verification flows. And TUF boot would download any supported artifact securely, given this kind of root of trust JSON specification. And then it would look something like this. So Linux boot starts, and now TUF boot starts executing. It receives a root of trust JSON file, and using the framework, it downloads the wanted file from an S3 bucket or HTTP or HTTPS server, then extract the OS image, puts it into RAM or disk, and then kexec, and off we go. So now it's the same benefits as before, but now we can actually do many more advanced trust delegations. Then now we have solved problem 2. Then third, remote attestation. So I was touching upon this already. So how can I in a centralized manner know that a decentralized machine is secure? It has booted correctly and hasn't been compromised. For example, this could be a case where centralized in the cloud, you have a machine learning model, and you want to have that machine learning model distributed to the edge and run there. But how can you know that because it's sensitive data in that machine learning model, how can you know that it's actually safe to distribute it? And remote attestation solves this problem. So a TPM, or Trusted Platform Module, is a dedicated microcontroller designed to secure hardware through integrated cryptographic keys. So it can generate keys, it can sign, verify, encrypt, decrypt data, and store platform configuration registers. And the PCRs, they are pretty special and useful. So the key idea behind PCRs is that they can only be extended, they can't be ever set. And there's the formula, but I won't go into that. But the good thing is as it only can be extended and not set, we can form now a way to seal and not just the data. So you, by sealing, you lock something, you encrypt something with both the key, with your own key, private key in the TPM, that never is leaked, never goes to the computer. And so you can encrypt using that key and the current state of these platform configuration registers. And to produce the same platform configuration registers, you need to provide exactly the same data in the exactly the same order. And this is called static root of trust measurements. This means that only if all boot binaries are correct in order when you boot, you can unseal a secure, a sensitive piece of data. So yeah, that I'll have a picture about how this works. So this solves the introspection of the boot flow. And remote attestation, now that you have this kind of PCR values, which if you would boot something malicious, then the PCRs would be completely different, and then you wouldn't be able to unlock the data that you had sealed, or unseal the data. So the challenger is a server in the cloud, and then the trusted platform here is on the edge with the TPM. And there is a nonce that is just a random number to avoid replay attacks. The nonce and the PCRs make up a quote, so-called quote. Then the edge device is sending the quote to the server, and the server can then verify that is this what I actually expect. So this is how it would look like in all in all. So the system on chip has on-chip read-only memory bootloader, and it, before running uboot SPL, it verifies what is the hash of this uboot SPL. So like the SHA-256 sum or something. It puts this into the TPM and says that this is what I measured the next boot step to be. And then uboot SPL measures Linux boot, puts that into the extends that to the PCR0 to the TPM. The hash changes. Linux boot does the same for the target Linux, and so on, so on. So this builds a kind of a chain of hashes of what has been booting next before actually executing the next thing. And this means that when we are in the target Linux and now your machine learning app wants to access the model from the cloud server, for example, then it needs to ask the cloud server for like what is a nonce that I need, and then what PCR registry should I look at, and in this case PCR0, and then generate some random number, gets that. Then the app asks for a signed PCR quote from the TPM. When it has the quote, it can send that to the server. The attestation server can verify that the quote actually matches the reference. So it knows exactly that, okay, if this is the resulting hash, exactly this on-chip ROM, this uboot SPL, this Linux boot, and this target Linux has booted. So if the service knows that now, then they can use the public key of the TPM, the machine learning model, and then send it over to the app and decrypt it in the TPM. So that is how this whole flow would look like. And now we have addressed problem 4, remote verification of the edge node. And here is some good resources on remote attestation, because it's pretty tricky to wrap your head around first time seeing it, but I promise it makes sense. Okay, so then on to the edge automation part. So I've been working quite a lot on Kubernetes cluster lifecycle, as part of my upstream contributions. And one of the things I was working on actually was that we would not be reinventing the wheel for Kubernetes management, because before everybody was. So this is actually a hard problem. Like if you have your own set of opinions and your own set of ways of doing things, how can you use some tools or building blocks such that you don't have to rewrite all of the things yourself for 100% of the kind of stack. So this is, we'll look into some solutions for that, because reinventing the wheel in terms of Kubernetes, that is a many year-long project. Interoperability between many different providers. So tasks like creating, upgrading, and auto-scaling clusters can be wildly different from, say, already AWS to GCP to Packet to your edge on-prem nodes. These are completely different kind of ways of managing this thing, and how can you get some consistency here? And when you have consistency, then you can declaratively control a fleet of edge clusters. If you would get consistency in how you manage them, then you can also say that, okay, at this moment, I want these nodes to do these things. And then in a declarative manner, and then that will always happen, because they will stay in sync with the kind of what is desired, the desired state in the cloud. And then 8 is keeping ingested edge data in sync with the cloud. So imagine you have some on the edge, you have some MQTT devices that produce data, like, for example, temperature measurements. And if you would have something that sends that to the cloud, but you would lose connections, what do you do then? Do you cache up to some period? Do you retry all the time? Do you discard the data? What do you do? And changing your application for each temperature sensor that you're going to use, that is quite a lot of work. So is there a better way to do this in a more generic manner, that you can keep stuff in sync with the cloud without having to change all of your applications? Okay, so when starting SIG cluster lifecycle with Kubernetes, which is one of the special interest groups, we identified essentially 3 layers: infrastructure layer, Kubernetes bootstrapping layer, and add-on layer. And we set off, because the middle layer was the most well-defined one at the time, we started with that. And how can we make something generic in that layer that takes you from having a machine, a VM or a bare metal machine or whatever, to having Kubernetes? And that is kubeadm. And then when we had kubeadm, we could proceed as one component and done. Then we could proceed to tackling the underlying challenge of cluster API, or tackling the infrastructure part. So what is the difference between kubeadm and a, so to say, end-to-end solution? So what you want is probably from the bottom to up, but you don't want to write it all yourself. So then you can start writing some parts, but then use kubeadm at least in the middle to get you on the way easier. So kubeadm wraps and is part of this more high-level solution. There's also K3s, which is a kubeadm-like deployment mechanism, but where all the Kubernetes components are integrated into one binary. So in kubeadm, they are run as containers, the different microservices of Kubernetes. But in K3s, they are, because they all are written in Go, they can be integrated into the same binary. And that, combined with removal of some features that you don't need at the edge, means a small binary footprint, which is good, and also a bit easier deployment. And this is a CNCF sandbox project. kubeadm is part of Kubernetes. Then K3s is a bit more opinionated than kubeadm, which means that it's easier to get going with, but it doesn't have the same amount of flexibility or extensibility. So now we have addressed problem 5, reinventing the wheel for Kubernetes management. Then cluster API, I started talking about this a bit. That is kind of the next logical step after kubeadm. So now if we have something that can get us from having a machine to having a Kubernetes cluster, now the next problem is like, how do we get that machine? And this is making the management of X clusters across Y providers simple, secure, and configurable. Or how can I manage any number of clusters in a similar fashion to how I manage deployments in Kubernetes? And when you think about it, for deployments in Kubernetes, you never create pods directly. You create deployments, and then there's controllers which make sure that the desired state in your deployment always is true, always is the actual state. And with Cluster API builds on a similar mindset. So if we can declaratively find that these are the 6 nodes that should exist in this edge cluster, and excuse me, and then if you declaratively define that, then there will be a controller that reconciles it. Okay, if there's only 5 nodes now, then I'll wake up one more node, power that on. And if there's if we change the desired state to only 3 nodes should be running, then it's gonna like turn off the 3 extra nodes. So things like that, but it's always a declarative, like we can see on the right here. And it has spec and it has status, so the normal Kubernetes API style. And with this now, you can do common management solutions for upgrades, auto-scaling, and repair, regardless of where it's running. So that's really useful. And then it allows for GitOps workflows, which I'll explore next. So with Cluster API, we can get interoperability between many different providers. Okay, let's go to GitOps. So GitOps is a cloud-native paradigm for managing infrastructure. GitOps, which is coined by Alexis Richardson, the CEO of Weaveworks, again, where I have worked for the last couple of years. The idea is that we can declaratively describe the desired state of all of your infrastructure in a version backend, like Git, but it can be other things as well. But the emphasis is versioned. And then have controllers execute towards that state. So say that you would put your DNS records in Git, and then you put that I want these different DNS records to exist. Then you do git push, and then you have some controller that looks at, okay, well, these DNS records don't exist at the moment. So I observe the landscape, then I diff the desired state and the actual state. So the desired state is 3 DNS records should exist, then actual state is no DNS records exist. And then I act. Then I create the 3 DNS records that should exist. So that is one example of the more general GitOps paradigm. And then this allows for better reproducibility, drift detection, mean time to recovery, control, and much more. So the principles of GitOps is that the entire system is described declaratively. So like in a YAML file or JSON or some other declarative format. Then the canonical desired system state is versioned in Git. So you can go back, you can see the history, what has changed over time, and find out kind of an audit log as well from this. Then approved changes by humans or robots can be automatically applied to the system. So in the case of DNS records, we can automatically, using some kind of API, the controller can actually create the DNS records, and then they will exist. You don't have to do it yourself. You just have to say to Git that I want these DNS records, and then they will be created. And then software agents ensure correctness and perform actions on divergence in a closed loop. So for example, say that there would be some DNS outage, then you could actually notice, the controller could notice this and notify you back that you said that you wanted these DNS records to exist, but now it seems like there's some outage because we can't access them. Flux is the GitOps engine for Kubernetes, and it's original GitOps implementation created at Weaveworks. It syncs the desired state from Git, Helm charts, or an S3 bucket to a Kubernetes cluster. So you put your Kubernetes manifest in any of these locations, and then hook up Flux, which is actually running in the Kubernetes cluster, and then your Kubernetes cluster will always have the same state as what you have in Git. It's extensible and contains many advanced features. It's a CNCF incubating project at the moment and has a large community, and also a good integration system around it. So, for example, Cluster API or Open Policy Agent for policy and these kinds of things. Then one really exciting new project that a coworker at Weaveworks made is Käldström, which is a visualization of Kubernetes and GitOps using OpenTelemetry. So Käldström listens to Kubernetes events that are emitted every time a pod is created, deleted, whatever. There's a new event object in Kubernetes created, and Käldström turns these events into OpenTelemetry spans. OpenTelemetry is a CNCF sandbox project, or OpenTracing is a merge of OpenTracing and OpenCensus makes up OpenTelemetry. And this plays really well with GitOps, because now if you have Flux, you can watch the life cycle of your Kubernetes state being synced by Flux. So say that you push that I want this application to run to Git, you do git push, Flux syncs it to the cluster, and then some minute after you see it in the Jagger UI, which is a CNCF graduated project that okay, this was created and it took this long, and all of these things happen. So it's really it's a good visual tool. So it looks like this. That okay, now the deployment has been applied, then replica set has taken 2 seconds to do something. It took 1 second to schedule the pod, then took 20 milliseconds to pull the pod, and and so on and so forth. So you can get this kind of waterfall visualization using Jagger and OpenTracing together with Kubernetes and GitOps. So that is declaratively controlling a fleet of edge clusters. Then finally, how do you keep these things in sync with the MQTT data, for example? You can do that using KubeEdge or Akri. KubeEdge is an open source system for extending native containerized application orchestration capabilities to host at the edge. So in plain text, that means that you can have devices at the edge. You install KubeEdge on those devices, and then it's going to handle the synchronization of the data between the cloud and the edge using some policies, but kind of automatically. You don't have to figure it out, and you don't have to change your application. So here is one of the architecture diagrams of KubeEdge, and it's quite a lot, but you can look at this later. But the key point is that you can run normal containers, so AI inference tasks or something like that, and you can collect MQTT data or HTTP data, and then it keeps these things in sync between the cloud and the edge. And here is a really good, impressive KubeEdge use case. The world's longest cross-sea bridge uses a lot of sensors and across that bridge, and then they use KubeEdge to keep these data in sync and do all kinds of ML and AI tasks. So now we addressed the last problem, 8, keeping ingested data in sync with the cloud. And so what now? I've talked about a lot of different things. And is it now that implementation is left as an exercise? Yes, but also no. Hopefully, well, I'm working together with a couple of friends on Racklet, which is one of the projects to put these things together that I've just talked about. And you can see the announcement of Racklet in this video here. And if you're interested, you can join the open source firmware Slack, or if you're interested in GitOps, you can email me, or in Racklet, you can email me at lucas@weaveworks. So yeah, we'll try to put these things together in a consumable format, and so that you can learn these techniques, these advanced techniques, in a seamless manner. So that's it, and thank you.